Hello, I'm George Shaw. I work in the IoT group. I'm part of the Retail Solutions Division, specifically working on our responsive retail initiative. Just a little bit of background about myself. I've been in retail technology for going on. I started at the MIT Media Lab, where I was working with retailers doing research into what technology could actually help their business. When I left there, I went to a company called Retail Next and ran their R&D group for a while. Intel, and they in the group here they call me the head nerd, so I think that's a nice way of saying that I'm technical. I'm not a manager. I'm a technical person. I'm a data scientist first, an engineer second, and only third am I a marketer or a salesperson. Hopefully you'll realize that you're getting some of the technical details sort of straight from the horse's mouth. With that, I'm going to switch modes here and jump into some slides. Okay, so my talk today will be about creating a digital view of bricks and mortar retail. How do we create that view? What are some of the challenges associated with creating such a view? What does that view buy us, and how do we take action on that view? What does it all actually mean, and why would we want to go about this, and what are some of the challenges? This will be a relatively high-level conversation in the interest of time, and I want to get from end to end. So I want to start at the very beginning and make it all the way through to what a platform that supports a digital view of bricks and mortar retail might look like. So we won't get into too much of the technical nitty gritty, but feel free to ask questions later, or you'll always be able to catch me offline. I'm sure my contact information will be made available. Before I start, just a couple of caveats. One, like I said, I'm not a marketer, so you'll see that there are a few marketing slides peppered throughout. Those will probably stick out like a sore thumb. Most of the other slides you'll see here were created by me, a nerd. And then also I speak with my hands, and so since you can't actually see me, you'll only be getting one channel of information. And it'll become apparent in a few minutes. I'll make a point about why that's actually important. So with that, go to the agenda. This is initial evidence of this is not a marketing slide, but we'll start with sensor fusion concepts, just what it means to do sensor fusion, and a little bit about what that looks like in a couple of different modalities. We'll talk about the data sources that are typically available in retail and what it might mean to fuse across those data sources, and how we can create this full digital view by fusing across those available data sources that are in retail, and then what it means to engineer a retail-specific system, a system that would be designed to help power the store of the future. So that's our rough plan for today. So to start, I think it's very important to think of sensor data as into a more complete data set. And you're shining a light on one part of a bigger data set. So, I mentioned that I speak with my hands and you can't see me. So you're getting one channel of information right now. You're learning something about what I'm trying to communicate to you. You're hearing what I'm saying, and you're seeing a visual that I put together. You're not actually seeing me. So that would be another channel, which would give you a more complete view into the reality that I'm trying to put forward. If you were here in the room with me, you'd get an even more complete view. Now, this applies equally when you're talking about any type of sensor. That sensor is a source of data in and of itself, but if you make this conceptual shift and think of that sensor as giving you some information, possibly noisy information, probably incomplete information about what it is that you actually want to understand, you'll think of these sensor streams a little bit differently. You'll take different action as engineers and data scientists when trying to understand the feeds from those sensors, and it'll open up a lot of possibilities where you might have a sensor whose output is less useful to you in the short term, but might give you some additional information towards what it is that you really want to understand. And so you can sort of build up this bigger understanding by shining lots of lights on the domain that you're looking to understand. So this is really just a conceptual shift, and it's a shift that I think we as technologists all need to figure out how to make and start moving forward in that direction. And lots of people already are. And I'll talk a little bit more about what that actually looks like here in a second. So this is a standard framework. This is not something that I came up with. This has been around for a while for understanding analysis of sensor data and how you can build up more understanding and more information as you go up in levels. For right now, we're going to talk mainly about levels 0 and 1, where level 0 is cleansing of the data and also aligning different data points in space and time. So this is a really important concept and a really important step, and something that has enormous power just in and of itself. One example might be if you have motion sensors positioned around an office building or around your home or around some large space. The signal from each one of those motion sensors tells you a little bit of something. It tells you maybe there was a person in this room or there was a person in that area. As soon as you align all of those motion sensors in space and also in time so that their timestamps are synchronized and you know where they are, you've calibrated somehow to understand where they are in space, suddenly these very low power, low impact motion sensors become a system for robust tracking. And all you've really done is align them in space and time. So this level 0 of sensor alignment is incredibly important. And then we get up to level 1 where you'll start to do things like object detection or tracking. In the example that I just gave, a simple algorithm in that space where you have motion sensors that are aligned in space and time, a very simple algorithm would be able to track across that, and that would be at level 1. And then as we go higher up the stack here, you get more understanding of a full scene understanding. This particular example came from the Department of Defense, so they have threat and impact assessment, but that's obviously not particularly applicable in retail. But the idea is now that you've understood the entire scene, now you can understand the impact of that scene. And so there are some obvious applications in retail. And then as you go up the stack, and I think the higher levels of this stack will probably be beyond the scope of this talk today. So there's a lot of formal work happening in sensor fusion, has been happening for some years. I don't want anybody to think that these are the two magic equations, and when you've memorized these, now you know how sensor fusion works. But these are just examples. I'm trying to illustrate that there is formal work that's happening here, and that formal work, a lot of it is centered around multiple sensors of the same events. And so that's the second example there, where if you have multiple sensors that are sensing more or less the same thing, a Kalman filter is a powerful way to integrate across those sensors. This is just an example of how to compute filter gain, and it really just illustrates that a Kalman filter, almost right out of the box with very little modification, can ignore or weight data from one sensor or another based on the noise or the variance that's present there. And then the top equation really just illustrates or touches on an illustration of the fact that more sensors are always better. There's no loss in data that's possible when you have more sensors, when you have more information. You'll always be better off because you can always ignore the new information. So there's no way that you can ever go backwards with more sensors, assuming you have some meaningful framework to know when to ignore the information that's not as good. And then down the bottom there is just some sources of more information. And Wikipedia, as any good nerd, is a great place to start. If this is a field that you know nothing about, that's a great place to begin. Of course, this is a paper. The second one is a survey paper. I by no means suggest that this is the only academic survey on the topic. There are many surveys on this topic. This one's a few years old now, but there's more. If you're interested, absolutely do a literature review. And then the Center for Multi-Source Information Fusion at Buffalo University is one of the only full research departments that I know of that's focused specifically on this topic. So that'd be a great place to go to look for more information on sensor fusion from a more formal standpoint, and to understand more of the mathematics behind it and how you might approach this field, as a data scientist or an engineer. So that was sensor fusion with typically more basic sensors that are seeing roughly the same thing. Sensor fusion in computer vision is typically a little bit different. You're often fusing across video streams in feature space to create one cohesive view. The intuition is that you have lots of cameras, and many of those cameras are seeing the same thing, and you want to be able to integrate across many of those cameras. So as an example, if you want to track people across cameras, this is something that you do in retail, and lots of other domains as well. A simple sort of naive approach would be to do all of your tracking, your person tracking, in the view of each camera independently, and then take those tracks and project them into one unified coordinate space. Create a homography that is able to project points from camera space into world space or feature space, and then you've got something like tracking across cameras. A better approach would be to project the view of each of those cameras into that unified space first, and then you can do your object detection, your person detection, and your tracking in that unified coordinate space. So you're able to leverage the views of disparate cameras in order to create one much more accurate view of tracking. Incidentally, this is the way the NBA does this. The NBA has a very difficult tracking problem that they've solved quite well, where they want to track all the players on the court and the referee throughout the entire game. So you have 10 people typically tangled up in a mess, moving very quickly, with motion signatures that are at the very least unusual. So it's a hard tracking problem. So they'll have some number of cameras over the court. It varies a little bit, but every professional court in the U.S. is outfitted. They'll have some number of cameras over the court, and they'll project the view of those cameras into a unified coordinate space so that they're able to perform this tracking in that unified coordinate space. Their projection problem is a little easier, because they're looking at a basketball court which has lines all over it, and makes doing the calibration and creating homographies much simpler. Whereas operationally in a retail store or out in other domains in the real world, it's harder to create those calibrations, but the approaches are very similar. This slide here sort of illustrates also that you might want to get different information from another camera. So maybe you want to track people using overhead cameras and understand their movements, but maybe you want to do facial recognition or understand demographic information from a camera that's got a different view, and then you might want to integrate those data points across cameras. The approach there is not different. The algorithms, of course, are very different, but the approach is very similar. You'll take all of your data from one domain, you'll project into a unified space, and then you can use simple algorithms or increasingly sophisticated algorithms to bring that data together. So in this case, you might project the facial recognition information that you've got into a unified coordinate system so that it's aligned in space and, of course, in time with the other cameras that are looking from overhead, so that you can say that this person who I've seen walking around is actually Bob, or is actually a male, for example. So that's the basic idea behind sensor fusion, to convey some concepts here and to give some sense of the depth. This is the furthest thing from an in-depth study of sensor fusion. We obviously didn't get into a ton of technical detail there, but it gives you some idea. So now I want to think about, in retail, how does sensor fusion actually play out? What does this look like in retail? What are the data sources that are available in retail, and how do we bring those together in order to create this digital view of the bricks and mortar store? So I'm going to look at crawl, walk, run. These are where things started out, where they've gone, and then where they're going. Crawl is point of sale. every retail store by definition has some way of collecting money, right? So there's always a point of sale. This is an area that's changing quite a bit. Payments are very different around the world. There's a lot of variability, in fact, but there's still some record of the transactions that exists. This has always been the case, back to the very start of retail when the transactions were written down on a piece of paper, up through more digital electronic systems, and even onward through things like staff-free checkout, where the point of sale is actually just automated. It's part of the store. There's still a transaction record, and that transaction record is an incredibly rich source of information, and one that you'll typically want to start with when you're aligning the rest of the data sources that are available to you in a retail store. Next would be traffic counting. This can be as simple as a beam counter, or even as simple as somebody standing at the door with a clicker. That actually counts as traffic counting and can be thought of as a data source. But then this goes up through IP cameras, monocular IP cameras. You see at the top left there, typically be overhead, right at the entrance. I myself don't walk into a retail store without looking up. Kind of drives my wife a little crazy, but I'm always looking at the traffic counters. That was a business that I was in. And so, I'm always kind of doing a survey of this. If you do the same, you'll very, very often see a traffic counter over the door in most major retail stores. From monocular cameras, you'll typically go to stereo cameras. This provides more accuracy with lower operational cost. They're very, very easy to install. You typically can stick a stereo camera on the ceiling and walk away. As long as it's got the right view, it'll do its own calibration. It'll understand its own environment enough so that it's able to make traffic counting assessments. The output of these systems is typically just a 1 or a -1 with a timestamp. Somebody walked in or somebody walked out. They'll a lot of times do tracking under the hood, but you won't typically see the output of that as a data source. So you'll get this very limited view. Back to the idea that we're shining a light on a bigger data set. This is a relatively small light. It shines only at the entrance, but it is a light. It gives you some sense of what's happening in the store. So traffic, along with the transaction log, again, assuming that those are aligned in time, can give you some idea of what's actually happening. 10 people walked into the store and 5 of them actually bought something. A retailer would call that 50% conversion. And that's the way a lot of retail stores today are managed. So that's why I say this is the walk phase, and this is the phase that most retailers are actually at right now, which is just traffic counting. We might jump to a run phase. Inventory tracking is running. RFID is by no means new, and I wouldn't typically call that running. It's not a forward-looking technology, except that doing it in real time across an entire store, to be able to understand exactly where each product is, where each RFID tag that's attached to a product is at any moment, in a way that's operationally viable. Retailers can support this, and also aesthetically viable has been one of the big challenges. Where many retailers, most retailers, in fact, are sensitive to how their stores look, and so as engineers and technologists, that's not often our first priority. We want to make a thing that works. Making a thing that works and looks good is often an asterisk, but in retail, that can sometimes jump up in importance, and it almost always jumps up in importance depending on the particular retailer. But that's why I say this is a run phase. Retailers are starting to adopt this. This is going forward in certain retailers. Intel has a responsive retail sensor that's out in the market now. That's a aesthetically somewhat pleasing, or at least neutral sensor that's able to do near real-time inventory tracking across lots of tags. Typically, a retailer will augment fixed sensors like the Intel one or others with handheld sensors, where they'll have store associates go around the store and wave the handheld around to get even another view into where their inventory is. As a source of data, is incredibly powerful. The thing that matters the most in a retail store after the transactions and how many people walked in are, where's the stuff. And so if you have a near real-time or real-time view of exactly where the stuff is, that can help enormously in understanding what's happening in the store and in taking action to improve the store experience and improve operations in the store. There are all sorts of sort of wins in this. So inventory tracking is one of the huge pillars, one of the big areas of development going forward, and something that's out in the world now. Next, I would jump to computer vision. Computer vision as a source of data is really king. It's not quite king yet, but I put it on that throne because this will be the most powerful source of data. Monocular cameras, every retail store has lots of monocular cameras already. The reason that those typically aren't used for analytics and more sophisticated approaches are more organizational in retailers. Those monocular cameras were typically put there not by the groups at the retailer that would be doing the kind of analytics that we're talking about here. But that can and will change. So leveraging these monocular cameras is incredibly important to us as technologists, and being able to use those cameras to generate meaningful data and meaningful insight is an area of very active research. I'm sure there's nobody on the line here that hasn't heard about a lot of the advances in computer vision, particularly around deep learning, which can do object recognition and person recognition and person tracking, facial recognition, pose estimation, a lot of different applications on monocular streams. To make those even more powerful, you can move up to a depth sensing stream. So you would have RGBD, where you have typical RGB video, but also with a depth channel so that the camera itself knows how far away things are. When I was talking about traffic counters, I mentioned stereo. Stereo is also a technology that's used here in computer vision, where you'll want to get some depth information in order to make the computer vision more powerful. For example, to do pose estimation, depth is incredibly valuable. Pose estimation in a retail store can be incredibly important. You want to know if somebody's reached out and touched a product, for example, and you want to know that at scale. You don't want to know that one-off by actually watching. You want to understand that situation at scale. So depth is a very powerful way to do that. I mentioned stereo. A lot of stereo cameras, like the RealSense camera that I'm showing here from Intel, will use a structured light approach where there'll be an IR projector, and the camera itself can understand how that IR bends and moves in order to better understand the depth makeup of the scene. There are other technologies like time of flight, where you're shooting out light and measuring how long it takes to come back, so that you can understand depth based on the speed of light and how long it takes that light to actually reflect. So with all of those streams of data, assuming we can bring them all together and assuming we can do the right things, I'll get to a little bit of that in a second, we are actually able to create this completely digital view of a store. So we understand the geometry of the store. Typically that's very easy. You might just get that from a floor plan. You'll understand the transactions that are taking place in the store, typically from the point of sale. You'll understand where all the products are in the store from a solution like an RFID inventory tracking system, which can also be married to enterprise systems in order to know which tag belongs on exactly which product. And so you can color the products accordingly, like in my visualization here. But the point there is you'll have a view of every product that's in the store. And then through computer vision, there are other means, but I think that computer vision is one of the more powerful means to understand where the people are in the store, and also to help identify in some fashion who those people are. And when I say in some fashion, there are different levels of identification that are possible, where you might want to just say, this is a store associate and this is a customer, and that's all the identification you'll want to do. Sometimes you'll want to go deeper and understand demographic information, for example, to understand who the shoppers are at a store. When that's married to tracking, typically from overhead cameras, or pose estimation from other computer vision sensors, now you have basically a complete digital view of a store. This is something that could be visualized easily as a video game. This is something that would be the output or the input from a game engine, something like Unity, is powered on the same kind of data that we've just been able to generate through RFID and engineering into point of sale system and computer vision. Bringing those together, we're able to do something like visualize a complete 3D environment with all the actors in that environment, with some amount of information about each of those actors and all of the movable assets like products or even shopping carts and so on. The main point here is getting to this level. We'll talk about how we can actually build some of these systems. Again, I'm not going to go into a ton of engineering detail here, but I'll give some high-level view of what some of these comprehensive system for retail might look like. What does the brain of a store actually need to do? What are the inputs? Well, what's the kind of logic? How does that all look? And what are the outputs? How does a brain like that actually affect the store? So for inputs, I'm gonna point to one of the few marketing slides that's in my deck here. But Intel has a set of technologies called context sensing SDKs. That actually should be plural. These are just a set of software tools for ingestion and management of sensor data. The context sensing SDKs are able to speak to a variety of sensors. There's some very large number of 500 plus sensors that are able to communicate with the context sensing framework. Many of those are applicable to retail and are valuable in retail. I put a URL at the bottom there. If you're interested to learn more, by all means, go to that website. There's a lot of documentation there. There's a lot more information. There are downloads and developer quick starts and so on. And again, if you get stuck and need more information, you can always contact me. So we've brought all this data in. We've generated lots of data. We've brought it all together in one place. We've ingested it somehow. What do we do with it? How do we go forward? How do we understand what to do with this complete view of a retail store that we've created? The very short answer is we ask the retailers. We shouldn't try to take guesses, and we as technologists, when I say we, I'm mostly counting myself as a technologist, shouldn't try to take guesses. We're not driving that. The retailers are driving that. So there's a couple examples there of some of the people in retail organizations that would typically be interested in these complete digital views of the store. They'll oftentimes have slightly different interests and different requirements and different things that they'd like to know given that store. Head of merchandising will often want to know how customers are interacting with products, how customers are acting around different displays and fixtures in the store. Store operations will often want to understand store associates and workforce management and where products are, inventory movement, and so on. Marketing, of course, will want to understand how effective store marketing is, how we can power new kinds of store marketing and those kinds of things. And then loss prevention, of course, wants to catch the bad guys. They might use a complete digital view like this to prevent theft or fraud of various kinds. So the bottom line here is that it's up to the technologists to, now that we've engineered a system and now that we've built these systems and we have an understanding of them, to go and ask the stakeholders, in this case that's the retailers, what it is that they'd like to know. Ask them in their language, in the language of business, and then it's up to us to at least help, if not to entirely translate their answers into technical requirements and into approaches that we can use to go and actually address these kinds of questions. So once we've got a set of questions in hand, we've got a data set that ostensibly can answer those questions, to think about what kind of technologies we can use. We don't want to go and manually answer these questions. Typically, we want technology that can address this. So this is a rough continuum. We could spend the next 4 hours discussing and debating exactly what the points are on this continuum and how they all lay out. But I think it's good to have at least a high level view, going from descriptive analytics at the far left, which is typically just counting how many people walked in, how many people walked past that fixture. Was there more than zero of this product on the shelf when people walked by? Very simple kind of counting problems like that. Next, I have data science in quotes because increasingly as the popularity of the term data science grows, data science is more and more inclusive. So data science at one point was the domain of PhDs and nerds in academia, whereas now data science is much, much broader. So I put it there, I put it in quotes, along with advanced analytics, where you might be doing somewhat more sophisticated mathematical modeling of what's happening in the store, trying to find correlations and so on. There are a variety of use cases for things that might be considered analytics. Again, it's a pretty fuzzy line between descriptive analytics and advanced analytics, but for the purpose of discussion, I think it makes sense to at least put some stakes in the ground here. Go up to machine learning, where again, fuzzy line in some cases where advanced analytics ends and machine learning starts. Deep learning being a subset of machine learning. These kinds of approaches can help you understand more complex behaviors. For example, I gave the NBA example earlier where the NBA is tracking players in the game. They might want to know what's the name of this play versus what's the name of that play. Machine learning could pull those kinds of higher level views out automatically. If you remember back to the stack of levels there, above level 1, which was object detection and object analysis, was scene analysis. Machine learning can be brought to bear on problems like that, where you've got spatial information, you want to understand what that spatial information means. So you could potentially train a classifier, train a network in the case of deep learning to know what it looks like when a customer is confused, for example. And given the data that's flowing in, again, that data may be integrated across many cameras or many sensors, and that data flows into some machine learning classifier or network and makes the determination either this customer is confused or not. So you can start to pull out higher level behaviors, and that's just one example. The sky's really the limit there. And then again, fuzzy line between machine learning and artificial intelligence, but most typically AI is thought of as being even higher level than that. So back to the NBA example, you want to name all the plays. Once you've named all the plays, maybe you want to understand the flow of the game. You want to understand the emotion of the game. And so that would typically be an AI problem. AI will often leverage approaches from machine learning, but typically AI will be thought of as more cognitive or further up that sort of scale. The quote here from Naveen Rao from Intel is the ability to find useful structure in data somewhat automatically. So that implies a smart system, a system that's able to look at data and understand which structures might be useful and try to make some sense of those higher level structures. One of again, the few marketing slides that I have here, I definitely am not going to dive into every piece of what's on here, but the takeaway is that Intel does AI. We have a lot of AI capability here. We're certainly not alone in this space, but we are leaders in this space. There's a lot of technology, particularly under the Intel NERVANA umbrella, that can be brought to bear on these kinds of retail problems. So we've generated lots of data. We've fused that data together into a comprehensive view by ingesting it into some framework and doing some sort of sensor fusion across modalities. We've figured out what the questions are that we want to address. We've brought to bear AI of some level of sophistication, some kind of mathematical modeling on answering those questions. So now we have answers. We have real answers. How do we bring those answers to the world? How do we take action? So we need some endpoints. This slide here probably doesn't do justice to the wide array of endpoints. This can be everything from BI tools that a retailer might use across their entire organization, where they want to see insights. In the example of confused customers. So knowing that you have a confused customer in aisle 4 on Tuesday can be useful. That might push to one endpoint that would ask a store associate to go and help that confused customer. That might push to another endpoint that counts how many times that happened in that one particular store and tries to make some sense of that. There might be some data mining involved where customers are more confused when there's a promotion being run or that kind of thing. And then that also might push to some higher level endpoint that aggregates across lots of stores. So if I'm the CIO of a 1,000-store chain, I'm not going to really care that there was one customer confused on Tuesday in aisle 4. What I'm going to care about is what's the rate of confusion across all my stores. Maybe I would want to look at that by department. Maybe I would want to bring that information to somebody else in the organization who could try to figure out why that is and try to move that needle. Maybe there's marketing messaging or wayfinding of some sort via an app, or there are lots of different ways that we could hope to affect that, and then we could go back and measure again. Associate empowerment was one that I mentioned, where there are systems now where a store associate can wear an earpiece, and that earpiece is powered by a system that sits in the back office, so that store associate gets an alert in their ear that somebody needs help, or somebody's asking for some inventory insight, or has some other question that associate might be able to answer. And that associate also might have an app on their phone, or they might be carrying around a tablet of some sort that can give them even more information. So you can imagine the use cases and the kind of abilities that start to open up when you brought all these different pieces together, all these different components together. When we're thinking about bringing technology into retail stores, the worst thing that we can do is think we're going to go invent all of it, and we're going to bring it all out there and put it in a retail store. There's an existing ecosystem. There's lots of technology currently in stores. There are lots of companies, big and small, that are bringing new technology into retail stores. And so as technologists that are hoping to create broader solutions, we need to think about that ecosystem first and foremost. And whatever solution we come to needs to take into account this ecosystem and ideally builds on this ecosystem. The ecosystem is a great thing. It offers retailers choice, offers lots of different functionality. It raises the bar across the board. So when we're thinking about how to build technology into retail stores, whether it's a single point solution or something much broader, we always have to think about what's the rest of the array of technology that's living in that store. So given all that, this is I'll put this in the category of a technical diagram with huge quotes around it. This is a very, very high level view of what such a system might look like. So inbound, you might have lots of sensors down at the bottom that are being ingested into some kind of a brain, which is managing those streams of data, fusing across streams, aligning in time and space, doing the kinds of things that we talked about around data fusion, actually creating that digital view of the store. And then the all important do stuff block there, which is where you might do business logic and you might have retail specific functionality. Things like, if a customer is confused, we should probably go do X, Y, and Z, and we should record that in some other table that's going to be offloaded later. And then you need some kind of outbound interface so that you can act on those results. And again, work within that ecosystem to leverage the technology that's already out there. And so at a very high level, the responsive retail, which is where I work and what I'm working on, does all of those things. We'll be talking a lot more about it at the NRF Big Show in January in New York. If you're at all interested in retail technology, I think you can't miss that show. And if you do happen to make your way to the show, by all means, come by the Intel booth and chat. I would love to talk more about this stuff. I could go on all day and discuss, any aspect here. But the NRF Big Show is where it's at for retail technology and retail in general. We'll be there talking more about our responsive retail platform. With that, I'm going to wrap up. Just want to point to the URL at the bottom. A lot of the topics that I just very briefly touched on here have a bit more depth on the Intel retail website. So by all means, go there, click around. I didn't put a comprehensive list of URLs here because it got unwieldy, but if you get to intel.com/retail, you should be able to find information about AI and sensor fusion and RFID and computer vision and so on, and some of the use cases that Intel's supporting and what some of the movement is around retail technology. And so with that, I'm going to stop sharing my screen and switch to question mode here. I'd like to thank everybody for joining us today. Hopefully this was helpful. And again, feel free to reach out afterwards. Thank you.